Hello, and welcome to a presentation on the fuel intake system of a hybrid car, presented by Ryan Marsden, Ryan Kirkpatrick, and Andrew Beam. First, some background on hybrid cars. A hybrid car is a motor vehicle that utilizes two or more types of power, usually a combination of a gas engine and an electric motor. Hybrid cars are often seen as a cleaner option when compared to gas motors due to rising emission standards globally. The hybrid car dates back to 1899, when its first iteration was developed by Ferdinand Porsche of the Porsche Motor Company. In the early 1960s, there was a push for automotive manufacturers to produce more efficient hybrid-powered vehicles in order to combat air pollution. This push became more prominent through the 1970s as the oil crisis became an issue and increased gas prices. In 1999, the Honda Insight became the first mass-produced HEV or hybrid electric vehicle, shortly followed in 2000 by the Toyota Prius. Here we have a comparison between a hybrid vehicle and a gas-powered vehicle. On the right, we have a gas-powered vehicle, with fuel entering the fuel tank, going through the fuel lines and the fuel injection system into the internal combustion engine. The energy produced by the internal combustion engine is sent through the transmission to the drive wheels, and the byproducts are sent through the exhaust system and out of the vehicle. To the left, we have a hybrid vehicle with a similar internal combustion engine. The difference between the hybrid vehicle and the gas-powered vehicle is that the energy from the internal combustion engine is sent through a power-splitting device that can either send the energy from the internal combustion engine directly to the drive wheels or through a generator to an electric motor or to a battery pack to be used later. Here is our problem statement. We are modeling the fuel system of a hybrid car using transfer functions. Now, there are multiple reasons why we should study this system, and there are several answers that we can obtain from the model. We can obtain the effectiveness of both the electrical and gas components on a hybrid vehicle. We can understand the effect that using a hybrid car can have on cutting down pollution, and we can understand the way that the two sources of energy drive the car and how all of those components could be improved. When looking at the modeling of our fuel system from a system dynamics perspective, the fuel system can actually be treated as a circuit. The circuit elements can be treated in series and parallel based on the layout and elements in the car, such as the parallel cylinders in the inline-4 engine. The circuit itself is a self-sustaining process that powers itself through its routine processes, meaning that there are no outside forces that need to be modeled in our system. Each element used in the design of a hybrid-powered vehicle can be modeled in a closed system, with an input of typically petrol or gasoline and an output being rotations of the drive axle or flywheel. The parameters of our system are as follows. Being a current system, we'll be working in the frequency domain. Since we're starting from rest, we will assume the initial values of everything are 0. The fuel entering through the intake valves will be assumed to be current and modeled as Q in. The cylinder wall resistance will be modeled as capacitance and be represented as C. The cylinder heads will be modeled as resistance, represented using R. The combustion of the internal combustion engine system inside of the cylinder walls can be modeled as a voltage source V and translated to the flywheel. The output of the system will be modeled as Q out and refers to the fuel or current exiting the exhaust valves to a ground. There are a few assumptions we can make that will make the modeling process easier. We can assume that fuel flow or current is constant. We can assume that the air-to-fuel ratio is constant, meaning that the throttle position remains the same. We can assume that the thermal energy released during combustion does not affect the voltage potential. We can assume that the frictional forces between the cylinder wall and the piston are negligible. We can assume that the crankshaft does not vibrate when rotating. We can assume that 100% of the exhaust leaves the system. We can assume that there are no carbon deposits on any parts or spots in the combustion chamber. We can assume that the battery, the spark plug, and the spark plug wires are all ideal. We can assume that the crank rod journals, or the pieces that connect the piston to the crankshaft, are at 90 degrees from one another. And we can assume that all of the mechanical parts are 100% rigid. Here are a few mechanical diagrams that we can use as references when modeling our system. We are modeling our fuel to charging system off of the 1.5 liter Toyota Prius engine. Now, in our modified circuit, the enclosed sum of currents ends at a common ground, which is the exhaust valve. When analyzing our modified circuit, the transfer function of Vs is equal to Q out over Q in shows a proportionality between the fuel being injected into the system and the rotational energy that was created via the combustion. In this Simulink model, it shows how the current or fuel of the system will travel through the network of resistors and capacitors. Now, all of the capacitors and resistors have equivalent values due to the fact that they all represent different parts of identical cylinders in a four-cylinder engine. Now, the equations for the quote-unquote circuit were derived using Kirchhoff's law and related the current flow to the fuel flow throughout the four cylinders of the Prius engine. And using Mathematica, we were able to derive the transfer function of Vs in terms of the wall resistance in R terms and capacitances in C terms. The capacitances of the system are assumed to be equivalent throughout each of the cylinders, and therefore the area of the piston and the density of the gasoline being ejected into the engine can lead to a constant C value being produced. Likewise, for the wall resistances, an R value was found to by definition of equivalent of resistance in terms of fluid systems, in which the 0.006 term refers to the standard dynamic viscosity of the gasoline, accompanied with the 0.0847 meter stroke of the cylinder. These values are small but not entirely negligible. These values were substituted into the original transfer function to obtain the Vs transfer function in terms of S only. In analyzing the fuel input to output ratio, the graphical model can be obtained comparing the efficiency of the system in terms of a percentage versus the fuel intake level indicated by the depression of the gas pedal, which injects more fuel into the engine. This analysis leads to the most efficient universal ratio being 1:1, which means the engine is running optimally at an intake level of 0.1261 liters per hour, as dictated by the data cursor on the graphical model on the next slide. In accordance with the data retrieved, the yield of the system demonstrates that the system is most effective in terms of fuel efficiency at the 1:1 marker. This is important to eliminate unspent gasoline or excess gasoline being released into the atmosphere, causing pollution. When converting the optimal fuel-to-air ratio, the conversion of fuel flow to RPM can be used in order to obtain a numerical value for the number of complete rotations that the flywheel makes at the optimal level using the fuel mass flow rate, assuming a linear power band. In the base 1.5-liter Toyota Prius, a power split transmission is used, which takes a percentage of the power generated from the rotational energy of the flywheel and converts it into both mechanical energy, the driveshaft turning, and the electric generator, converting the rotational energy back into potential energy, or voltage. In accordance with the power split transmission, Toyota estimates that in ideal conditions, 51% of all input through the transmission is converted into electrical potential energy. Using standard information regarding the power splitting transmission provided by the manufacturer, the internal Toyota Prius battery will charge at a rate of 4.353 volts per second at the ideal operating fuel ratio. The charging system charges at a rate of 122.5 over 6.5 volts per rotation at an ideal efficiency of 51%, and when multiplied by the ideal condition of 1,630.5 rotations per minute of the flywheel, the resulting charging output of 4.353 volts per second is returned to the high output battery. There are a few key takeaways from this modeling. This modeling is the key to analyzing efficiencies of engines to reduce emissions. It can also be used to analyze the full cycle of a system to predict longevity of the battery. It's also important to analyze the system for fuel economy purposes and can help manufacturers produce automobiles using baseline systems altered from the Prius base engine. It also defines correlation between fuel flow throughout the system and rotational energy being converted back into usable voltage during engine processes. In conclusion, Using key assumptions as well as provided conversion factors from the manufacturer, the system was able to be modeled as a closed-loop process. Fuel intake was modeled as a voltage. Cylinder processes were modeled as resistances and capacitances, resulting in an input-output ratio. That input-output ratio was then analyzed in order to calculate the ideal operating fuel consumption rates. And then that fuel consumption rate was converted into RPM of the crankshaft using standard operating parameters of the 1.5-liter engine. Then those revolutions of the crankshaft were multiplied by the charging rate in order to return a voltage being provided back to the internal battery of the Prius, thus creating a charging cycle. And here are our references.